You're working on training a machine learning model using the BreastMNIST dataset to classify breast lesions as benign or malignant. The goal is to improve the model's performance while keeping it simple and efficient, avoiding unnecessary complexity like ResNet architectures unless needed. The code is being updated to better handle tasks like saving training results, generating Grad-CAM visualizations, and converting the model to a web-friendly format for deployment. You're also transitioning from Flask to a lightweight JavaScript frontend to reduce server load and streamline user experience.
How big is the ResNet model? Currently what we have, the Keras model that we have at the moment is 134 megabytes. How much bigger ResNet would be or is?
The size of a ResNet model depends on the specific variant. For example, ResNet 18 has around 11 million parameters. ResNet 50 has about 23 million, and larger versions like ResNet 101 or ResNet 152 have even more. In terms of file size, ResNet 18 typically ranges between 40 to 80 megabytes, while ResNet 50 can go up to 100 megabytes or more. Comparatively, your current model at 134 megabytes seems larger because it might include additional metadata, stored weights, or overhead from saving it in the legacy HDF5 format. A properly optimized ResNet 18 might actually be smaller than your current model, but ResNet 50 or larger would be significantly bigger, likely exceeding 200 megabytes.
So what do we currently have in the model saved that makes it so large? And can you specifically explain, like say ResNet 18, what its exact size is and the model complexity and the reason for it having that many parameters?
Your current model is likely large due to factors like high-resolution input images, 224 by 224 with one channel, the saved optimizer state, and additional metadata included in the H5 or Keras format. Saving in these formats captures all weights, model configuration, and sometimes training states, which can inflate the size significantly. Additionally, large dense layers, even in simpler models, contribute a lot to size since each connection requires a weight and a bias. For ResNet 18, the model is relatively lightweight in terms of parameters, approximately 11 million, but its size and storage is influenced by the precision of weights, usually float 32. This typically results in a size of around 40 to 50 megabytes. Its complexity comes from its architecture, which introduces residual blocks to address vanishing gradient issues. These blocks add skip connections, allowing the network to learn more effectively in deeper layers without drastically increasing the number of parameters. Despite this, ResNet 18 is efficient because it uses fewer filters per convolutional layer compared to larger ResNet variants, balancing performance and size.
So do you think it's worth doing a comparison of the current model we have to ResNet 18?
Yes, it's worth comparing your current model to ResNet 18. ResNet 18 is lightweight for a residual network and could offer better performance due to its deeper architecture and residual connections, which are effective for extracting complex features. By comparing, you can evaluate if ResNet 18 achieves higher accuracy or AUC on the BreastMNIST dataset while maintaining reasonable training time and model size. If ResNet 18 performs significantly better without adding excessive overhead, it might justify the switch. However, if your current model is already close in performance, sticking with it could save time and resources. The key would be to experiment and directly compare metrics like training time, validation accuracy, and test performance between the two models.
Can we take the original data file and we would like to generate instructions for pre-processing, training for the whole pipeline? Because we're getting a bit stuck up in thinking starting from scratch. So back to the original compressed BreastMNIST 224.npz file.
Starting from the original compressed BreastMNIST.npz file, here's how you can approach building the pipeline from scratch. This considers all elements we've discussed, including pre-processing, training, evaluation, and deployment. 1. Loading and inspecting the dataset. First, load the .npz file to access training, validation, and test splits, train images, train labels, etc. Inspect the dataset to confirm shapes, label distributions, and pixel intensity ranges. This ensures the data is as expected. 2. Preprocessing. Normalize pixel values to the range 0, 1 if not already done. Add a channel dimension to reshape images to 224, 224, 1 for grayscale inputs. Handle class imbalance using techniques like oversampling, undersampling, or synthetic data augmentation for the minority class. Ensure preprocessing steps are consistent across training, validation, and test datasets. 3. Data augmentation. Use an augmentation strategy for training data to improve generalization. Apply transformations such as rotation, zoom, width-height shifts, and horizontal flips. Balance this to avoid overfitting to augmented patterns. 4. Model architecture. Start with a simple CNN, similar to your current model, and refine it if performance is unsatisfactory. Include convolutional layers with increasing filters, max pooling layers, and dense layers with dropout for regularization. Optionally, compare this with ResNet 18 or another lightweight architecture. Save this model in .Keras format for compatibility and modern standards. 5. Training configuration. Use a standard loss function like binary cross-entropy and metrics such as accuracy and AUC. Include class weighting if there's an imbalance. Use Atom as the optimizer with a starting learning rate of 0.001. Add early stopping and checkpoint saving to avoid overfitting and ensure the best model is saved. 6. Evaluation and metrics. Evaluate on the test set after training. Save metrics like accuracy, AUC, confusion matrix, and misclassified examples. Plot training and validation accuracy loss over epochs to analyze learning progress. Use Grad-CAM to generate interpretability visualizations for correctly classified and misclassified samples. 7. Deployment preparation. Convert the trained model to TensorFlow.js format for deployment on a web interface. Address any issues during the conversion process, such as weight naming conflicts. Test the converted model with sample inputs to validate correctness. 8. Front-end integration. Design a web-based visualization similar to your rhythm scan tool. Include options to upload images and view model predictions. Display results like confusion matrices, performance metrics, and Grad-CAM heat maps. Optimize the interface for usability and ensure smooth client-side interaction. 9. Performance comparison. If needed, train ResNet 18 using the same pipeline and compare its performance with your current CNN. Compare metrics like test accuracy, AUC, training time, and model size to decide if switching is beneficial. 10. Iterate and optimize. Based on initial results, tweak preprocessing, model architecture, or training configurations. Use feedback from evaluations, e.g., misclassified images, to refine the model further. This approach builds the pipeline from scratch while incorporating all discussed enhancements, ensuring a clean slate and a clear progression toward a deployable solution.
Yeah, what expert normally will be reviewing this type of data and making a diagnosis?
BreastMNIST data is typically reviewed by radiologists if it represents imaging like mammograms, focusing on patterns indicating benign or malignant lesions. If the data is histopathological, pathologists examine tissue samples for cell abnormalities. These experts work together, often alongside oncologists, to ensure accurate diagnoses and treatment plans. If you don't have access to an expert for a second opinion, and the cost is a concern, you could consider using an AI-based diagnostic tool as a supplementary option. Tools like those trained on datasets like BreastMNIST can provide insights by classifying images into categories like benign or malignant. However, these tools should never replace professional medical advice. Other options include accessing online platforms where radiologists or pathologists offer affordable reviews, or consulting healthcare programs that provide second opinions at reduced costs. Local teaching hospitals or medical schools might also have initiatives where supervised trainees review cases at a lower expense. AI tools should not replace professional medical advice because they are meant to assist, not act as final decision makers. While AI can provide helpful insights, it may not fully account for the complexities of individual cases, such as patient history, other diagnostic tests, or subtle variations in data that experts recognize. AI systems can also make errors, and a medical diagnosis has significant consequences. That said, AI can still be incredibly valuable as a supplementary tool, especially in regions with limited access to specialists. It can guide users on when to seek professional opinions and support experts by flagging areas of concern. But the ultimate diagnosis and treatment decisions should come from trained medical professionals.
Never say never.
You're right. Never say never. AI technology is advancing rapidly, and with proper validation, regulatory approval, and ethical oversight, there might be scenarios in the future where AI plays a more primary diagnostic role, especially in underserved regions or for triaging cases. For now, the best practice is to treat AI as a powerful assistant that enhances rather than replaces human expertise. With continued development, AI might one day bridge gaps where specialists are unavailable. But until then, collaboration with medical professionals remains key.